So while I'm getting set up and we wait for a few more people, completely by chance yesterday, I was reading just browsing some stuff on the history of vaccination. And I knew it was old. I knew that, hundreds of years ago, people had been vaccinating against smallpox by doing something where basically if a person has smallpox, they take some of the pus from one of that person's smallpox scars and they would transfer some of it to another person to give them a minor smallpox infection. You might think, well, is there such a thing as a minor smallpox infection? Apparently getting a tiny amount of smallpox through a wound and getting it from another person mixed in with their pus, which has antibodies. Apparently getting it through a wound is less dangerous than getting it through inhalation directly to the lungs. So they would do that, and it greatly increased the odds of survival, a preemptive smallpox vaccination. Now, I knew about that. What I didn't know is just how old it was. It was only discovered by Europeans about 300 years ago, but apparently it had been used in Africa, India, and China much longer than that. And here's the real kicker. The first person to introduce inoculation into the United States was a slave in Boston. There was a smallpox outbreak, and he had been born overseas, and so he knew how things are done there. And he told people what they would do to deal with smallpox. And his owner was Cotton Mather. The slave's name was, they gave him some elaborate Latin name that I always have to look up. It's hard to pronounce. It was, let me see. Cotton Mather, I know because he's a rather famous Puritan leader. Onesimus. It was not, that's not actually an African name. It's apparently some Latinate name given by his owner. But anyway, Onesimus came up with it. They come up with it. He was well known where he came from. He informed people in Boston of it and probably saved Boston. And somehow his name isn't on hospitals. You would just sort of assume that given that he saved Boston by introducing the oldest form of inoculation to the New World, to Western world, that he would have his name on hospitals, but nope, because, he was treated like shit. But anyway, that's how old vaccination is. It's been done, well, they didn't call it vaccination, they would call it inoculation for using a more innocuous type of infection to prepare you for the nastier infection. Anyway, I was completely unaware of how it came to Boston. It's well worth reading about. Just Google for inoculation, Boston, smallpox, and things will come up. Nothing else take away that, damn it, vaccinations work. People have been using them for hundreds of years. And we should be getting on with our lives once we're vaccinated. That's why I'm really not worried about in-person classes, because vaccinations work. And the vaccinations we have are way more targeted than anything that people had long ago. Any questions? Questions about fall classes and policies and whatnot? Any questions about the distributed Bragg reflector project that's due on Thursday?
I don't know if it was mentioned last week, but how would you set up the partial log plot? Do you do that directly through Python?
The semi-log plot, how would I make it?
Yeah.
I would just go into Excel and put the make the vertical scale logarithmic. And as for how you make that plot, I mean, you can't, the Python program that I've given you as it stands cannot do a whole bunch of systems of different lengths and put them all on one plot. You would just have to run it for a system of a given size and look at the reflectance or transmittance and say, okay, at this wavelength, what's the transmittance? And then input the parameters for a system of a different size, look at the transmittance plot and zoom in on the plot and say, okay, at this wavelength, what's the transmittance? And then put all that into Excel and make a semi-log plot.
Oh, okay. Thank you.
Mhm. Other questions? All right. So last time we were talking about diffraction gratings. Remember, the basic idea of a diffraction grating is that it's a periodic system and you send in light, and on a distant screen, the light forms a series of peaks. And where these peaks are is determined by the wavelength. And the positions of these peaks are given by, if this was the center one, this would be at theta equals 0. This would be at theta greater than 0, theta less than 0, and they satisfy the relation d sine theta equals an integer times the wavelength of light. So sine theta is m lambda over d. And that's how essentially almost all modern measurements of the wavelength of visible light and things near to the visible spectrum are accomplished. For very high energy photons out in the UV, sometimes they'll still use gratings, other times they'll just have the photon impart some energy to an atom or an electron and then measure the energy and deduce the wavelength that way. Out in the microwave regime and lower frequencies, longer wavelengths, they might measure it by just directly measuring the frequency of the wave. But for anything in the visible or visible adjacent regime, they almost always use diffraction gratings. And I put the word almost in front of it, not because I'm terribly aware of exceptions, but because if I don't, someone will find an exception. All right, so we talked about that. And all right, you can use this to measure the wavelength of light. And we talked about how it basically stems from the fact that if we look at the waves coming from different slits, that path difference is d sine theta. The path difference between this wave and the wave, between, say, the wave from down there and the wave coming from the slit one above it, is d sine theta. And if all of those differences are one wavelength or two wavelengths or three wavelengths and so forth, then everything adds up constructively. Well, we're already familiar from things we were doing a few weeks ago with situations where waves produce constructive interference peaks. What's different about a diffraction grating is that we're used to getting patterns that look more like this. You get the patterns that have a peak and the secondary peak, not just sharp spikes with essentially no light or barely any detectable light in between if it's a decent diffraction gradient. And it's worth spending some time on that, both because it's just a really interesting phenomenon to get that kind of concentration of light. And it's also worth asking, well, just how concentrated is the light? All right, the more concentrated it is, the more precision you have in doing measurements. So the basic idea is that each slit is just, well, it's a slit. It's got a width A, a separation D. And so we're really just summing up over all of the slits, which I'll denote with the subscript J. sinc Ka over 2 sine theta e to the I k d sine theta times j, an integer, right? Because we're either over here or 1 up or 2 up or 3 up and so forth. Let's call this, yeah, we'll stick with that. All right, so I'm going to call this phi, and this thing is the same for all of them. So I can pull it out, sinc Ka over 2 sine theta, sum of e to the I phi raised to the power j. And j will be from 1 to n, or maybe I should say from 0 to n minus 1 to do this right. And I said last time that we could think of this as just adding up a bunch of numbers in the complex plane. So here's j equals 0, j equals 1, 2, all right, so we're just adding up a bunch of these. And if we add up enough complex numbers that are all of the same length and more or less evenly spaced, well, then they have to add up to 0, or if not exactly 0, because I don't have exact cancellation, I have ever so slightly more of one than the other, something very small, something very close to 0 compared with the bright peaks over there. Let's try to make this a little bit more rigorous. Let's start with the case if phi equals 2 pi times an integer plus 2 pi over n, the number of slits, because that's the number of things we're adding up, plus 2 pi over n, big N. Little n will be an integer. You got big M, and then I need another integer, so I'm just going to call it L, because why not? Just another integer. E to the I phi is e to the I times 2 pi n, e to the I 2 pi L over n. What's this factor out here? The e to the 2 pi I n. Don't overthink it. Come on.
1.
What?
1.
Thank you. So what I'm left with is this. And if I add up n of these, I'm either going to make 1 circle around or 2 circles around. It all depends on whether it's 2 pi over n or 4 pi over n or 6 pi over n, but I'm going to make some circles around, okay? So sum of e to the I phi is just the sum of e to the I 2 pi over n, big N times L. All of that, and all of that should have been raised to the j. All of that should be raised to the j. And all right, I'm going to either be making 1 circuit around, 2 circuits around, 3 circuits around. And we know that that case, it's 0. What if it was just a little bit different? Then I would still make basically a circuit, another circuit, and then I might have a few extra. If I have a few extra to add up, we don't care. Adding up a few extra complex numbers, we usually have thousands of these because D might be, say, 10 to the minus 6 meters. And the overall size here might be 10 to the minus 3 meters or larger. So we're usually gonna have 10 to the 30s. Adding up a few more, we don't care, all right? Even if they all added up perfectly constructively, over here, you're adding up 1,000 ones. And your intensity is proportional to E squared, which is proportional to 10 to the 6. If I was somewhere like here, and I have a tiny residue, let's say I got 10 of these left over. Which is much less than 10 to the 6 or a million. Everybody okay with that logic? All right, so if the phase shift going from one slit to the next and so forth is 2 pi, is some multiple of 2 pi over the number of slits are close to it, we're going to get either perfect cancellation or almost perfect cancellation. But here's where it gets a little more interesting. What if phi is equal to 2 pi n plus pi over big N, right? Then the sum of e to the I phi raised to the j power would be a bunch of evenly spaced complex numbers that only go out to there, all right? They only go halfway. And so we can see that we're clearly going to get, we're clearly going to get something that doesn't cancel. You might say, well, if it was a little bit bigger, well, now we're starting to get some cancellation. Which is why, which is my justification for, this is a different color. I want to know when things don't cancel. And I already know one case when things don't cancel. D sine theta equals m lambda. I want to figure out when else things don't cancel, because as much as I've drawn these as just little spikes surrounded by nothingness, if we actually zoom in on the intensity profile, it's not little spikes surrounded by nothingness. It's more like this. If I zoom in on it, I've got a spike surrounded by things that get smaller, and they get smaller very rapidly. And then there's another spike surrounded by things that get smaller. And the spike has some non-zero width. And I care a whole lot about the width of that spike. Because what if somebody sent in, I could say, all right, well, you know, here, sine theta equals lambda over d. Hey, we just measured lambda because d would be provided by the manufacturer of the grating. You determine this based on the pixel that it hits. You say, hey, great. But what if somebody sent in ever so slightly different of a wavelength, which I will draw in a different color, even though in reality it would. And I want to know, hey, am I going to be able to tell that I have two different wavelengths, two different kinds of light hitting my detector? Right? That's the question I want to ask. That's the question that experimental physicists want to ask most of the time. Most of the time it comes down to, well, not, there's plenty of things. One of the many, many important questions that experimental physicists want to ask is, whatever I'm detecting, am I detecting one thing or two things? Two things. Am I detecting one phenomenon or two phenomena? That's what we want to understand. We want to figure out, are these two wavelengths producing overlapping things or not? And we could say that we could see that we're still getting some kind of effect. You might say, well, you know, this one and this one, the one that went all the way to the right and all the way to the left, they're canceling out. So we're starting to get some cancellation. But on the other hand, we still got some reinforcement. Like if I look at this one and this one, which I've drawn longer just to highlight them, yeah, they're horizontal parts, their real parts cancel, but their imaginary parts add up. So we're getting some partially constructive interference. Partially constructive interference means we're not right here at the peak, but we're also not down here at 0. We're somewhere like there. Any questions on the idea that I'm trying to get at here? What I'm basically doing is I'm trying to look for an intermediate case that would be like right on the edge of the peak, not all the way at the top, not all at 0, and figuring out when do we see that? Because if we know when we see that, then we can figure out how wide this is. And I maintain, just based on the fact that we get partial cancellation, that it's when phi is not an integer, well, an integer multiple of 2 pi plus pi over the number of slits. All right? And if I work with this condition, I get that kd sine theta equals 2 pi m. I should have put m there because that's when we would have a peak, plus pi over the number of slits, or 2 pi over lambda d sine theta equals 2 pi m, forget about that, plus pi over n. All right. Start by canceling the pi's and the 2's. And I'll put a 2 in the denominator there. And I'm left with d sine theta equals m lambda plus lambda over 2n. Now at the peak, d sine theta peak equals m lambda. So what we have here is d times sine theta peak plus delta sine theta. What do I mean by delta sine theta? Some people think, oh, is that sine of delta theta? Not necessarily. Sometimes it is, but we're not going to assume it. That's not guaranteed to be true. All right. We're just saying that, well, we would measure the value of sine theta at the peak. You know, if this horizontal axis here were sine theta, here's the value of sine theta at our peak. And then we move out a little bit to the right, and we just change the value of sine theta. Let's see here, d sine theta peak is equal to m lambda. So those cancel. We're left with delta sine theta equals lambda over 2 n d. Any questions? Somebody must have a question. What I'm basically saying is if we could do a really high precision measurement, zoom in on, oops, peak right there. That oops. Here would be sine theta peak. Here would be the edge of it. Sine theta equals m lambda over d plus lambda over 2n d. And then if you went out to there, sine theta would be m lambda over d plus lambda over n d. That's the entire idea of it. And we can verify this. We can go into Mathematica. There's a file I posted last week. I'm going to share my other screen. It's a file I posted last week. And we can indeed see things like that. And we can see that the pattern has a peak. And I've plotted this versus theta rather than sine theta, because it's probably a little bit more intuitive. You can see there's a peak and then there's secondary peaks and it decays. The width of this peak is inversely proportional to the number of slits. That was in the formula we wrote down. Delta sine theta is lambda over nd at the 0 here, and lambda over 2nd at this point right here. Let's verify that. So I'm going to zoom in on this a little bit more. I'm going to plot this from 52 to 54. And by the way, all I did to calculate this is I just defined a function that simply adds up all of those exponentials. That just adds up e to the I kd times sine theta times an integer. And then I divided by n slits squared so that the peak will always be 1. All right, and we see that this peak goes from about 53, or maybe it's 52.9 to about 53.25. So that width is, well, from 52.9 to 53.25, that's about 0.35. Let's see what happens if we double the number of slits. Hey, it gets narrower. Now it goes from about 52.9-ish to about 53.1. So it went from 0.35-ish to a little bit below 0.2. From 0.35-ish to a little bit below 0.2, that's roughly cut in half. Any questions? Let's zoom in a little more and see if we could do this more accurately, precisely. So, okay, looks now like the peak was probably not at 52.9, but about 52.95. And the dip was at, well, not 53.3, but maybe 53.25-ish. So from 0.95 to 0.25 is a width of about 0.3-ish. And now from 0.95 to 0.1 is a width of about 0.15. Any questions? Somebody must have a question.
I think I'm missing the big picture.
We're just, go ahead.
Sorry, like I know earlier you mentioned about how we want to see if two waves are sort of overlapping.
Mhm.
I'm guessing that's something similar to like resolving two different objects or something, right? I
It's
don't know.
similar to what?
Resolving like two different objects in case like they interfere with each other. I don't know if I'm using the right terminology.
It's along the same lines. There are some differences because now things are separated, not like their actual positions in space, but they're separated by having different wavelengths or different frequencies. But in both cases, you're trying to resolve two peaks. Let's look at the case below. So where you've got a spectrometer with 400 slits, okay? N is 400. And we send in light with a wavelength of 0.532 or 0.532 microns or 532 nanometers. And then we send in another one with a wavelength that's 532 nanometers plus one more nanometer. And we just want to look and see, all right, how much light would we get at each angle? And we see that when we run the calculation, we have to sum up 400 slits, so it's going to take a second. Or more than a second. When we run the calculation, we get two distinct peaks. That's very good news. We've got a peak at one angle and a peak at another angle. And as long as our detector was good, you know, that we'd have to, these things are traveling just a fraction of a degree apart. So you'd have to let the light travel a long time to spread out so that they hit, the two peaks hit different pixels. But as long as they hit very distinct pixels, you could say, okay, however much light I get here, that's from one wavelength. However much light I get there, that's from another wavelength. And then you could do a very precise measurement of those wavelengths. Does that make sense?
Yeah, that part I get. Could you sort of, I guess, go back to the first plot, like why we were investigating
This one, why we care about the width?
Slits. Yeah.
Well, with this one, we were just trying to see how the width depends on the number of slits.
Oh, okay, okay.
And then here, I'm showing what happens if we have a grating with, say, 400 slits. If the grating has 400 slits, then we get two peaks that are far enough apart that we can resolve, we can tell the difference between 532 nanometer light and 533 nanometer light. And there are a lot of places in chemistry and material science where you want to do that. There are a lot of places in chemistry and material science where a change in the wavelength or energy of a photon is telling you something about the change in the energy of an electron or the change in the energy of a chemical bond. And you really want to know that because that's telling you something about what's actually going on in the material. But you can only do that if you have something that measures wavelength precisely enough. Does that make sense?
Yes, thank you.
So let's see now what happens if I speed up this calculation. Do it with 100 slits. Oh, wow. Now we have a mess. This is why we cared about understanding how the width of this peak depends on the number of slits. Any other questions?
So sorry to refer to what you just said. So we could sort of use that guide, the relations between the width and the number of slits as to help us differentiate if we may be looking at multiple peaks just sort of in one.
Well, let's put it this way. If we have a low resolution spectrometer, if our spectrometer would take one, suppose that you have a spectrometer that you send in a pure signal, one wavelength, not a combination of two wavelengths, just a very pure signal. And it produces a peak that's spread out over about 0.4 degrees. And then on the other hand, we have this thing where we send in two signals. And again, we get this blob that's spread out over 0.4 degrees. And you might say, but it's slightly lower there. Okay, well, if we had really, really good detection, maybe we would see that. But if we have a highly pixelated, a coarsely pixelated detector, then we're not going to see this dip. We need to know that if we see something that's 0.4 degrees in width, is that because that's as good as our detector can do? Or is that because there's actually two signals separated by 0.4 degrees? You see? If I made this separation there. So now let's look at this scenario where we've got two wavelengths separated by half. We've got two signals separated by half a wavelength. Sorry, half a nanometer. We got two signals separated by half a nanometer, and they produce one peak, okay, with this width. Well, I could go up here and I could send in, I could have, again, 100 slits, and I'm going to plot, I'll plot it the same as I did down there, from 52 to 54. 52 to 54 up there, 52 to 54 down there. These two aren't on the same scale because I didn't magnify them the same. But leaving that aside, can you really tell the difference between these two graphs with your eyes?
Well, I mean, using the axis as a guide, I mean, one clearly goes a little bit higher, but I guess not.
But how would you know? I mean, okay, I've normalized this so that if we have one peak, its height is 1. How would you know that here we have one thing coming in and here we have two, instead of maybe in this case, we've just got one wavelength, but the thing is a little bit brighter, okay? Maybe we have a brighter object producing 532 nanometer light. Could you tell the difference between those two options?
No, definitely not.
In principle, you could look over here and see that it goes to 0, whereas over there it doesn't. But in almost all cases, there's noise in these detectors. And because of the noise and because of the fact that the pixels have finite size, so it's not like you get to say, okay, how much light is coming in at 53.100 degrees and how much light is coming in at 53.102 degrees or something. You almost never get to do that. And so if we could do that, then we might look and say, oh, but you see here, it doesn't quite go to 0. And there it does. In principle, you could do that. But in practice, because your detector is never that finely pixelated, and because there's always some noise in the signal's always fluctuating a little bit, we're never going to be able to tell the difference between this one and this one. At most, you could say, well, this one's definitely brighter. So either we've got one source of 532 nanometer light, but someone turned it up, or we've got two sources of light at very, very close wavelengths. That's the most you could possibly tell. That's why we care about all of this. Other questions? a substantial portion of what people do in chemistry is try to figure out whether an absorption or emission line has shifted by a fraction of a nanometer. Things like Raman spectroscopy, which is basically a type of spectroscopy that probes vibrational transitions in a molecule, or things like nuclear magnetic resonance, where, okay, it's not a nanometer shift, but basically they're looking to see how have the energy levels of the nucleus shifted. And the energy levels of the nucleus depend on the s electrons, the electron orbitals that, that have some non-zero density in the vicinity of the nucleus. And so you're looking at very tiny, tiny shifts of a transition line, because a tiny shift of a transition line is telling you something about the bonds. It's telling you something about the environment that the electrons and atoms that the electrons form are in. That's why understanding the mechanism of the precision here is important. Let's get a little more quantitative about that. Let's try to derive a formula. I've given you the idea. I'm going to share my other device and we're going to write some notes. All right. So we know that the width of this thing, or let me rephrase that. Let me redraw that. From here to there, delta sine theta is lambda over nd. The width is that. Two lines are distinguishable. People always say resolvable, but I think distinguishable makes the case better if separation is greater than lambda over nd. If they're separated by more than that, then at least in principle, they're distinguishable. Now, the signal may be noisy, the pixels may be choppy, there may be plenty of other reasons why you can't distinguish them, but at least the wave nature of light is not getting in the way. It's all the other things that are getting in the way. All right. So let's see here. What is the separation? So d sine theta d lambda tells us how much sine theta changes if we send in light with a different lambda value. Okay, well, we know that sine theta is equal to m lambda over d. So d sine theta d lambda must be equal to m over d. Which is bigger for bigger m values. So if m over d, wait, that's just d sine theta d lambda. That's just the rate at which sine theta changes. So delta sine theta due to lambda change, to lambda changing, not the number of slits, equals m over d delta lambda. Any questions on what I did there? So I need m delta lambda over d to be greater than I need that to be greater than lambda over n d, the line width. Because you can only tell the difference between, you can only tell two things apart if their separation is bigger than their size. Well, we cancel the d's in the denominator, and we are left with delta lambda must be larger than lambda over mn. Any questions? Well, at this point, it seems like, okay, we surely want two things. We want a lot of slits, and we want to work at large M. So many slits. So we want probably this grating, not this grating. Right? We want the one like this, not the one like this. But remember, there's a little bit more to it than just buying a wide grating. You could go to the grating store and tell the grating salesman to bring out their finest selection. And then you plop down your gold card and purchase their finest, largest grating. And it's so big that you have to load it into a truck. Okay. But what if your light is not collimated? All right. What if your light beam is small? If your light beam is small, well, honestly, you're not getting the full advantage of either one of these gratings. So we need to expand the beam, right? But you also need collimated expanded beam, because if I have a really messy beam, I could have a really wide grating, but I've got some light coming in like this and some coming in like that. And then we no longer have d sine theta equals m lambda, because the calculation we did before, that was assuming that everything comes in parallel to the axis, hitting the grating head on. And if things aren't hitting the grating head on, then all bets are off. So we definitely need collimated expanded beam. The theory of gratings isn't going to help you here. You just need to work on the optics that we're sending that light to the grating. Some people then say, well, okay, fine, we'll expand the beam. Well, some people say, okay, but we surely want large M. Well, all right, so we send in our light parallel to the axis. And on our distant detector, it forms many peaks. Here's the M equals 0 peak. You're never going to be able to distinguish that because every wavelength produces an M equals 0 peak. Here's your M equals 1 peak. Here's your M equals 2. You might say, okay, we surely want this one. And then you might say, hey, you know what? I'm going to be really clever. I'm going to use a large grading period, okay? So D, the slit spacing, will be large. Okay, well, if D is large, then we get something that looks more like this. We get our M equals 0 spike, M equals 1, M equals 2, M equals 3, M equals 4, M equals 5, and so forth. And down here, we'd have M equals -1, -2, -3, -4. And we're feeling so proud of ourselves because, hey, we've got M equals 5. So delta lambda is lambda over M, and we just made M big. Delta lambda is going to be really minimum resolvable. The minimum resolvable delta lambda. Our precision is lambda over M times N. We feel so proud of ourselves because instead of having 1 or 2 peaks, we went up to 5. We just improved our resolution by a factor of 2.5 using the same geometry, which I'm attempting to draw to the same size. Does anybody see a problem here?
Does it relate to their intensities?
Well, that's one of the 2 problems. So expand on that a little bit. Go on, you're on the right track.
I mean, based off of your drawing, it looks like their intensities are kind of hard to distinguish from each other.
Well, that's just my bad drawing.
Oh, okay. Well, I don't know if you have, I mean, I don't know how much larger that grading period would be, but will we no longer really experience that sort of interference from, you know, a smaller spacing that we traditionally learn about diffraction? Sorry, I don't know.
No. If your light is collimated, interference effects can show up even over many, many meters. People are building a 30-meter telescope, and the performance of the 30-meter telescope is, to the best of my knowledge, if they do it right, it will be well understood in terms of wave optics. So that's not a problem.
Okay. So does it actually have to do with intensity though? Because you.
Yeah, because we'll think about it. First of all, I've just divided the light among more lines. I've just divided up my light. So yeah, maybe I'm getting a smaller resolvable wavelength, maybe. But hey, I'm now getting less light out. So noise is now a problem. But
does it also have to do with when you're increasing your grading period D, you're also getting fewer number of slits, so N goes down?
Well, that all depends. Yes, if I increase D, but I keep size the same, or I keep the overall size the same, then N drops. Okay. So there's no free lunch here. N will drop if I increase D, but keep the overall size the same. So it's not always as good as it sounds. I could rewrite the equation. Delta lambda minimum resolvable equals lambda over mn. I might rewrite this, keeping in mind that n equals this length L over D. All right, I could rewrite this as lambda D over ML. And then I could remember that D sine theta equals M lambda. So M is equal to D sine theta over lambda and I could write this as lambda D over D sine theta over lambda. And then there's an L. So I take all of this. The D's cancel. And I'm left with lambda squared over L sine theta. So what I really want here lambda is given, whatever kind of transition, whatever kind of system we're studying, it is what it is. Lambda is given. I want a wide grating and light deflected through a large angle. Okay, those are the things I want. Wide grating and light deflected through a large angle. Now, it turns out that actually we can even do better than that. Let's start by talking about a reflection grating, because we're going to talk about that change of angle, and then that's going to have some implications for what that's going to lead us to how we solve the intensity problem. All right, so a reflection grating. You're actually familiar with the concept of a reflection grating if you've ever looked at a CD or a DVD. CDs and DVDs are these plastic things that we used to use to store movies and music before we got everything from the cloud. So you can look at them. They're in museums nowadays. I'm only sort of joking. I assume you've seen them, and you're looking at reflected light, and it obeys the gradient equation, right? And the way to understand it is I'm going to draw the incoming light like this. And then I'm going to say that that's coming in at an angle theta I for incoming. And I'll do the reflected light in a different color. This will be theta R. Well, let's see here. The top one travels farther to reach the grating. But then it travels shorter to reach the detector, right? Because if I compare this path, nor this one, with this path, the bottom one clearly has to travel a longer distance to reach the detector once it's left the grating, but it traveled a shorter distance to get to the grating. And everything we've done so far, the path length difference is always d sine theta. But now there are two thetas because there are two paths. The incoming path difference is d sine theta I. The outgoing path difference is d sine theta r. And so d sine theta I minus sine theta r is equal to m lambda, right? All the same things apply. And so now I could say that I could replace sine theta with sine theta I minus sine theta r. Our minimum resolvable delta lambda is equal to lambda squared over L sine theta I minus sine theta r. If I look up here, what's the largest value that the sine theta in the denominator could have? Don't overthink it.
It has to be less than, oh wait, you said
Less than
larger?
or equal to 1.
Yeah.
But now, sine theta can only be between -1 and +1. So what if this was 1 and this was -1? You see the opportunities here? You see the potential there? You could get a factor of 2 improvement. You could send this, it won't be exactly 1, but you could make it close to 1, and we can make this close to -1. That arrow just means approaching. So this one's almost 1, and this one is almost -1. We can make our denominator larger. Now, you might not choose to work at the extremes of the geometry, but what I'm trying to get across is that it's the change, it's how sharp of a reversal in direction you get. How sharply you reverse direction determines how good your resolution is. If the wave changes direction by a lot, then you can get sharper resolution. It's very much like what we found when we talked about diffraction limited lenses. All right, with diffraction limited lenses, if we have light coming in focused like this, we found that our spot size was 0.6 lambda over sine theta. And so if theta was really big, meaning that this top ray here changed direction by a lot to get there, then we can have a fairly small spot size. But if theta was small, if we narrowed the aperture so that one of our rays only changed light by changed angle, changed direction by a little bit, well, you don't get as small of a spot size, okay? You get big effects, which often mean very small spot sizes and good resolution if you force a wave to change angle by a lot. The most interesting interference effects almost always happen when waves either change angle drastically, either 90 degrees or even just turning around 180, or there's another kind of thing that you can get when they barely change direction at all. But the most interesting things always happen in the extremes. Any questions on that? Okay, so I've set up the concept of a reflection grating. Let's do one more thing and then we'll take a break. We still have the problem that light is going into many peaks, all right? We still have the problem of many, many peaks. But I've just been kind of playing fast and loose with the fact that when we add up all of these things, we're adding up the diffraction pattern of a single slit, which in this case was sinc Ka over 2 sine theta. So what I would probably want to do is, in this reflection grating, I could just have reflector and hole, reflector and hole. That's one possibility. There's a thing called a glazed grating. I don't know where the word glazed comes from, but the idea is that you've got these reflective grooves. All right, so you basically etch some grooves into a surface, and then you coat them with metal. Coating things with metal is actually really easy. You just basically heat up a metal, and well, I shouldn't say it's always easy, because depositing smooth metal films on weird surfaces can be difficult. But depositing smooth metal films on many materials, if the surface is relatively smooth, is often easy. You should always be very careful about statements like, oh, this material science process is easy. But oftentimes there are tools available to do that easily. So you just heat up some gold, so I wouldn't use gold, sorry, heat up some silver or whatever metal you choose to work with, and it will form a vapor. And then you just have whatever surface you need to coat with metal in that chamber full of this metallic vapor. And in a vacuum chamber, just put it in a vacuum chamber full of metallic vapor, and the metallic vapor will adhere to the surface. All right, so glazed grating. Now, why would we want a glazed grating? Well, suppose someone has done the math and they have determined that for this pair of angles here, we will get really good resolution. Theta I equals theta R if measured with respect to the normal to the groove, okay? So as far as things are concerned with the normal to the groove, it's just the ordinary law of reflection. But of course, these two paths are interfering when they come to the detector, right? And so, this, I've just happened to draw these going horizontally because it's an easy thing to draw. But I'll call this theta naught. We know that there is a path length difference here. And this path length difference will be d sine theta naught. D sine theta naught equals m lambda. So what we do is we take advantage of the fact that there are two different angles in play here. There's the diffraction angle, the change in angle looking at, there's the angles measured with respect to the normal to the overall grading, okay? There's the fact that, this path has a different distance than this path. And so we can figure out what this difference here is. And that has to satisfy the grading equation. More generally, d sine theta n minus d sine theta r equals m lambda angles measured from normal to the grading. But meanwhile, we know that these surfaces, being highly reflective, are going to behave like little mirrors. And we know that these mirrors are going to preferentially send light in a direction that is, these mirrors are going to preferentially reflect light like mirrors. And so if they preferentially send the light like this, and these two beams, and we've just chosen all the angles so that these two beams are interfering constructively, hey, we're in luck. We're going to get a really strong signal going at that angle. And this is how glazed gratings work. Any questions? All right, I've been talking long enough. I've explained the principle of a diffraction grating, how it is that you get sharp spikes. I've explained how we determine just how sharp those spikes are. I've explained the criterion for how sharp is sharp enough. The range of angles that the spike covers should be smaller than the change in angle that you would get if you change the wavelength of your input. And then I talked about how to concentrate all or most of the light at the desired angle instead of having lots and lots and lots of spikes at different angles. To go much farther with that, to learn about diffraction gratings, we could tighten up the theory a bit. Born and Wolf is a great place to go for that. But beyond that, the problem of the diffraction grating is a manufacturing problem, which I say not in any way to slight it, but simply to make the point that theory only takes us so far. If you really want to know more about this, then you have to look at, okay, well, what are all the things that people actually do to make these? And that requires a whole different skill set. Let's take a 10-minute break and then we'll start talking about photons. All right. Now we are going to start discussing photons. So we spent the first part of the semester saying that light is just a bunch of rays that travel in straight lines. Then we said that light actually spreads out like waves, at least if you look at it up close. And that was all of these phenomena that involve light behaving like waves are most apparent if you look on the small scale. I know I said earlier that even a 30-meter telescope exhibits wave phenomena, but keep in mind that with that 30-meter telescope, you have light from a distant star, so it's coming in basically straight lines. It's hitting the two opposite edges of the telescope. It's hitting then a mirror and getting focused. The wave behavior is only apparent in the pattern where the wave gets focused onto the detector, and you might still have to look on the detector on very small scales comparable to the pixel size in order to really see the wave nature of light. Well, people have found that if we look not just on small spatial scales, but on small time scales, we see even more interesting behavior. Here I show the ideal two-slit experiment. Interference patterns, bright and dark spots. But if we look on very short time scales, we don't get a nice steady flow of energy into the detector. It's not like if you just keep looking on shorter and shorter times, you get less and less energy. Well, you do get less and less energy, but it's not like as you look at it on smaller times, the amount of energy just keeps on decreasing nice and smoothly. Eventually, you look on a really small time scale, and you start to notice that it's clumpy. And on a really, really short time scale, you either get a little tiny packet of energy, you get an amount of energy that would correspond to one transition of one electron, or you get nothing. And then you watch it on another time scale, which may be nanoseconds or less, and you either get an electron, you either get a transition, an electron gaining some energy, or you get nothing. Something, something, nothing, something, nothing. That is what it means to say that light exhibits wave-particle duality, to say that it is a wave, but it is also a particle. If you look at how it spreads out in space, it's a wave. If you try to measure how much energy you're getting at a given instant in time, either you're getting something because some photon came in, gave energy to an electron, caused a transition, or you're not getting something. And those little particles of energy, those little clumps, they're often called packets. Well, their energy is related to the frequency and wavelength of the field, of the field pattern. So if I look at this and I say, okay, well, it's spraying out like a wave with whatever wavelength and whatever frequency, then the energy of each little particle will be Planck's constant, 6.626 times 10 to the minus 34, multiplied by the frequency, nu or f, not omega, or hc over lambda. So red photons have less energy because they have longer wavelengths and the energy is inversely proportional to wavelength. Green have more, blue still more, and violet still more. Any questions so far? So if we look at the electromagnetic spectrum, well, we can start to make sense of a few things about light and the kind of damage it causes or doesn't cause. So radio wave photons, microwave photons, they have very low energy. Infrared photons have somewhat more energy. Visible light, still more. Now, ultraviolet, the energy is significant here. The energy is large enough that you could actually rip an electron off of an atom, not just take an electron from the ground state to the first or second excited state, but actually rip it off entirely. That's what it means to say that it's ionizing radiation. Some ultraviolet, depending on the molecule, ultraviolet light might ionize. Even if it doesn't ionize it, it can do it can do more things because it has more energy. There are more possible transitions that it can excite, and so it can cause more damage. That there are more ways for it to cause damage to an organic molecule. That's actually one of the main reasons why ultraviolet light can cause skin cancer, and why it can sterilize the surface, why sunlight exposure is actually a great way to sterilize something. It's not a fast way, but my grandmother told me, my grandmother was a nurse in the Army during World War II, and they didn't yet have, they had the germ theory of disease, but they didn't yet understand sterilization as well as they do now. They didn't yet have all of the tools for sterilization that they had now. So what they would often do is they would have people who had been badly wounded, they would take off their bandage and have them sit outside in the sun. She was fighting in the Pacific front, not the European front. So they had plenty of sunlight. They would have them sit out in the sun. They would remove the bandage from the wound and expose the wound to sunlight for a while. And that would help keep the wound sterile. Ultraviolet light excites more transitions, can cause more types of changes in the molecule. X-rays now are ionizing, are highly ionizing. They can remove inner shell electrons. And then gamma rays are the types of electromagnetic waves, or the types of photons that are emitted during nuclear transitions, when the nucleus goes from one energy level to another. And those are even more damaging because, again, there is more energy per photon. This is also why hot objects tend to look red, and if they get hotter, they actually start moving towards bluish. This is why the blue part of a flame is actually the hottest. This is why objects at room temperature don't glow red, but they do glow in the infrared. And then as you heat them up, they glow red, and then they glow whitish, and then they could potentially glow really, really bluish. Any questions so far? All right, so given that these transition, that the wavelength and frequency of a photon correspond to the energy of the transition that occurred when the photon was emitted, you can understand then why different elements and compounds are associated with different spectral lines. And this is why spectroscopy is so important. This is why high precision measurement of a photon's wavelength is so important. But I just spent the first half of this class session talking about how would we get a grating with really, really good precision. All right, now here are spectra of different important objects. Here's the spectrum of the sun, which looks pretty continuous. They basically took the spectrum going from red to blue and zoomed in on it. And they zoomed in so much that just a segment of the red spectrum covers half the screen here. Another segment covers another half the screen. And it looks like it covers the whole visible spectrum pretty evenly, except that there are these missing lines, most of them due to either elements in the sun's outer layers or absorption lines in our own atmosphere. Now, this is a highly zoomed in picture. There's enough wavelength precision that you can actually see the missing lines. As you can imagine, somebody had to illuminate I don't know off the top of my head how big this diffraction grating was, but I'm comfortable saying in technical terms that it was freaking huge. Here's a more zoomed out spectrum of sunlight at ground. I spend a lot of time thinking about fluorescent molecules, not single atoms, not solids either, but molecules. And molecules tend to have much wider emission lines. And they tend to have also wide absorption lines, okay? Because there are many different transitions that can be stimulated, many different transitions that can be excited. But what do you notice about the difference between DAPI, FITC, and Texas Red? I forget what DAPI stands for. FITC is fluorescein isothiocyanate. It's related to, have you ever been, has your eye doctor ever done a fluorescein stain on your eye? So a fluorescein stain is they take this yellow dye and they put a drop of it on your eye. This is not where they dilate your eye. It's not where they put in those eye drops that make your eye really wide and you become really sensitive to sunlight. This is a stain that goes onto the surface of the eye. And then they shine a slit lamp on it. They look at it with a slit lamp microscope, and they're usually shining a blue light onto your eye. And they're looking to see how that fluorescein has accumulated on the surface of the eye. Which parts of the surface of the eye has it gone to? Those fluorescein stains are for assessing cornea problems. And I actually had, okay, funny story. So grad school, I studied optics. In the most stressful part of grad school, I got a terrible, terrible infection in my cornea and suffered permanent damage. And it was the price I paid for knowledge. The price I paid for knowledge of light was that I lost my ability to fully resolve information from light with my eyes. It's quite operatic. I feel like some figure from Wagnerian opera. I gained wisdom at the cost of vision. But anyway, I was getting fluorescein stains all the time. I also was using fluorescein in the lab for some of my experiments. And anyway, what do you notice about the difference? If you look here, okay, these are the absorption spectra. These are the emission spectra. What do you notice about the difference between the absorption and emission spectra?
The wavelength is shifted higher.
Yep, the emission spectra is at longer wavelengths than the absorption spectra. So the energies of the emitted photons, are they higher or lower than the energies of the absorbed photons?
They're lower.
Yep, longer wavelength, shorter, smaller energy. Now there are many things that fluoresce, fluorescent marker dye, fluorescent light bulbs. You can stain a cell with different fluorescent dyes, just light emitting molecules that are tagging a particular part of the cell. You can even engineer animals nowadays to express fluorescent proteins. A fluorescent protein is just, well, it's a protein. It's one of the things the cell makes. And a fluorescent protein is usually just a regular protein that has a little extra piece added to it, and that extra piece glows. And it was first discovered in jellyfish, but you can insert GFP, green fluorescent protein, into any animal these days. It's commonly done in mice and certain types of fish, but you could do it to any animal. I'm sure someone's done it to a monkey by now. And someday, some hideously unethical scientist will insert green fluorescent protein into a Homo sapiens. The fluorescent molecules tend to have these combinations of ring-like structures, these conjugated ring structures, alternating single and double bonds. Those are often very good for getting fluorescence. Fluorescent proteins have a very different kind of structure. They look more like, this is often called a barrel structure. It's kind of like a cylinder. There's green fluorescent protein. That's what they discovered in jellyfish, but nowadays there's a whole zoo of fluorescent proteins. People are actually more interested in red and infrared fluorescent proteins than green, even though green looks really cool. Any guess, or yellow, yellow also looks really cool. Any guess as to why? Ever shine a flashlight through your hand?
Yeah.
What gets through your hand? Does all the light get through?
No.
What gets through?
Red light.
Red light. So if you want to look at something that's going on deep inside of an animal, good luck getting blue light through that. I'm sure there's some weird invertebrate out there that transmits blue. I say that not because they exist, but not because I know them to exist, but besides my usual caveat about if I don't say that, someone will find an exception. Biology is remarkably good at that. Just last week, I read a science article about weird viruses that have a fifth DNA letter, a Z instead of an A. So there's probably some weird invertebrate that transmits blue and absorbs red. But you know what? For mammals, vertebrates in general, red has a hell of a lot better chance getting through. So a lot of work is done on infrared fluorescent proteins. But you know, people can make fluorescent proteins of the whole rainbow spectrum, depending on what it is that they're trying to do. And there's even wider rainbow of small molecules. I call them small because, well, to a physicist, any molecule larger than dihydrogen is a big molecule. We can handle dihydrogen. We like simple, clean systems that we can do elegant math on. But to a chemist and biologist, these are fairly small molecules, whereas proteins, those are the big molecules. But they would classify these as small molecules. And most of the work there is not so much on trying to achieve a particular color. By now, the whole damn spectrum is covered. It's usually about, okay, well, can I get something that not only produces this color, but will work very nicely in this type of environment, whether it's very high pH or low pH, high salt concentration, low salt concentration, whether it's a fatty environment, a very non-fatty environment. Is it something that's going to do well in the cell membrane? Is it something that's going to change its optical properties, its emission and absorption properties, if we apply a voltage to it? Voltage sensitive dyes are very nice things for neuroscience, and also I'm sure for some kinds of muscle physiology and heart research, because nerves are basically electronic devices. And so studying electrical signals in nerves is important. If you could see a color change, I mean, they already have ways to do electrical measurements, but if you could correlate your electrical measurements with your imaging, that would be really nice. All right, here's the key diagram for understanding fluorescent molecules. Although there are lots of energy levels, there's actually just two main electronic energy levels, all right? Here's one orbital. Here's another orbital. Everything else could be in the ground state orbital and have a little bit of vibrational energy, or have a little bit more vibrational energy, or still more vibrational energy. It could be in the first electronic excited state and have no vibrational energy, or a little bit of vibrational energy, or a little bit more. And vibrational transitions are very, very fast, usually. Optical transitions have lifetimes of nanoseconds, which means that you might have to wait several nanoseconds on average before a molecule emits a photon to go from this energy level to that energy level. But vibrational energy transitions, loss of vibrational energy, happens usually on picoseconds, sometimes faster. And so vibrational transitions are fast, which means that you got something hanging out in the ground state, absorbs a photon. Almost immediately, it will lose energy, right? And once it loses energy due to vibration, then it's going to sit here for a while. It could sit here for nanoseconds, which isn't a very long time for you, but is a very long time for a molecule. The electrons are traveling around the nucleus on, like, let's see here. They're going at like less than a femtosecond, all right? And the period of oscillation of the light wave is a femtosecond or less. And so it hangs out here for basically eternity as far as a molecule is concerned. And then it emits. And it could emit into any of these vibrational levels, and then it'll rapidly return to ground. And so that's why they almost always fluoresce at a longer wavelength than they absorb at. Hence the diagrams here. And this is called a Stokes shift. Not that you're going to need it for any test or anything, but if you do anything with fluorescence, you will see this term Stokes shift all the time. Any questions on this? All right, skipping ahead, there's one other thing I wanted to show about this. There's actually even more states. There's your ground state, various excited states. There's actually two kinds of excited states. There are triplet states and singlet states. Now, singlet and triplet, the difference has to do with the spin of the electrons. You'll learn about that in the upper division quantum mechanics course when they talk about the state of a system of two spins. If you've got two spins and you form combinations of spin states, you can either have singlet or triplet states. And singlet-singlet transitions, the ground state is, in all the cases I'm aware of, singlet, but I'm sure that there are some weird molecules with triplet ground states, probably involving magnetic effects that I've never given any thought to. But in all the standard fluorescent molecules I'm aware of, the ground state is a singlet, and the excited state that's most likely to get raised to is also a singlet. Occasionally, though, they get raised to these triplet states. And these triplet states are very long-lived. They're long-lived because it's difficult to move between singlets and triplets. It's difficult to get from a singlet to a triplet, and it's difficult to get from a triplet to a singlet. And so if it hangs out here for a while, other things will eventually happen. Excited states are reactive states. Chemical reactions are usually easier in the excited state. One reason why is that, well, if the ground state were reactive, that would kind of mean that it would be really easy for the ground state to change into something else. But the ground state doesn't want to change into something else. It's the lowest energy level. That's a very crude heuristic, but it can get you a certain ways in thinking about these things. So if it gets raised to a triplet state, it's likely to get damaged. It's likely that something else in the environment will come along and damage it. However, if it does go from a triplet state to a singlet state, if it does get into that triplet excited state, the return to the ground state could be microseconds or longer than that. And that's called phosphorescence. And that's why there are sometimes phosphorescent toys, because those excited states are so long-lived that you might actually, some of them could be on the order of seconds. There are also multi-photon processes. We'll discuss these later. These involve the absorption of multiple photons to get from your ground to an excited state. All right, I already explained the concept of fluorescence microscopy. Here are some pretty fluorescence pictures. Really just Google fluorescence microscopy cell biology and do a Google image search, and you can look at pretty pictures all day long. At this point, I'm going to stop. Next time, I'll talk about absorption spectra of different substances, and we'll talk about why it is it's hard to get light into an organism. And then we will talk about multiphoton microscopy. Have a good day.
Thank you, Professor.
Mhm.
I have a question.
Okay.
I'm trying to help my boyfriend who's doing research with Dr. Salik. Do you happen to know any resources regarding diffraction grating simulations?